Okay, let's try and actually prove something. The claim is if a graph has an odd length circuit, then it has an odd length cycle. So let's see what this claim even means. Take a graph that looks like this and consider the following circuit. Well, let's call this U, V, W, and Y. So if we look at the circuit U, V, W, Y, V, U, you'll notice that this is a circuit. It starts at U, it traverses a path, it ends up back at U, but it's not a cycle because we've repeated the vertex V here. But the claim says that if the graph has an odd length circuit, then it has an odd length cycle. So what's the length of this cycle? It's 1, 2, 3, 4, 5. 5 is odd. So this graph should have an odd length circuit. And it does. You can see it. V, W, Y, V. That's of length 1, 2, 3. There's a length 3 cycle in this particular graph. It begins and ends at V, and it doesn't repeat any vertices. On the other hand, if you took, say, this graph, let's call it U, V, and W, then any odd length circuit in this graph should correspond to an odd length cycle. I don't see any cycles in this graph, so there better not be any odd length circuits. So if we try and go from U to V to W to V to U, what's the length? Well, it's 1, 2, 3, 4. It's an even length circuit. And our claim says nothing about even length circuit. Our claim says that if you have an odd length circuit, then there's an odd length cycle. But you won't find any odd length circuits in this particular graph. So even if I go just U to V and back to U, that's a circuit of length 2, which we aren't even going to be considering in this course anyway. Okay, so how do we actually formally prove the claim? Well, we're going to do it by induction on the length of the circuit. So what's the base case? So I guess we should say P of n is a graph with odd length circuit of size n has an odd length cycle. And we want to prove that for all n odd greater than or equal to 3, P of n is true. Right. Remember, we're only considering circuits of length 3 or larger. So what's the base case? The base case is P of 3. P of 3 says a graph with an odd length circuit of size 3 has an odd length cycle. Okay. So you'll notice that the only graph that has a circuit of size 3 is a triangle. There's no other way to get a graph with a circuit of length 3 unless you're drawing a triangle. I mean, you can try drawing something like this. You'll see that there's no circuit. The smallest circuit has length 4. 1, 2, 3, 4. So to get a circuit of length 3, you have to draw a triangle. And that's good news because a triangle is a circuit. Or I should say a triangle is a cycle. Right? If this is U and V, W, then you go to V. You go from U to V. That's 1, 2, 3. It doesn't repeat any vertices, so it is a cycle. So U, V, W is a cycle. Remember, in this particular case, there are no odd length circuits, so it's not a base case that we have to consider. This is the only base case, the only case of a graph where you have a circuit of length 3. So how do we actually do the inductive step? I'm going to give you the main idea, and then we'll sort of formally write the proof. So remember, this is what we need to prove, that a graph with odd length circuit of size n has an odd length cycle. So we need to show, we're going to use strong induction. So we need to show that P3 and P5 and so on and so forth, and Pn implies Pn plus 2. Remember, we're trying to prove that for all odd values of n, the predicate above, P of n, is true. So we'll start with a circuit C that has length n plus 2. Okay, so it starts at some vertex u0 and it ends at some vertex u0. Now the thing to notice is, well, let's say that we don't see any other, that no vertices inside this circuit are repeated. Okay, if that's the case, then this is a cycle and we're done. Let me say that again. So if there are no repeated vertices other than, u0, then by definition we have a cycle of length n plus 2, and so we're done. There's nothing to prove. Now the other case is that we see a vertex repeated here as we move from u0 to u0. So let's say we see vertex, I don't know, let's call it vertex v star sitting here. And then we keep moving on this circuit and we see another vertex v star. So what do we do in this case? We need to prove, so we have a circuit, it's of odd length, it's of length n plus 2, and we need to prove that there's some cycle in the graph, odd length cycle in the graph somewhere. Well, how do we apply our inductive hypothesis? Well, notice there are actually two circuits here. There's the circuit that starts at v star and ends at v star. Okay, let's say that that circuit has length L. And then there's the circuit that starts at u0, it goes to v star, it skips this, and it continues on to u0. So it starts here, it goes to v star, it skips all this, and then wherever, right here, it continues on after this v star, and it ends up at u. Okay, and so I'll call this, these two segments, we'll say that they have length r. So the one thing to notice is that L plus r has to equal n plus 2. So the length of the entire circuit is n plus 2, and the length of these regions here have to therefore add up to n plus 2, and we have this region in between v star and these two v stars, that's L, and then we have this region right here, sort of going from here to here and then continuing on here. We said that has length r, so L plus r must equal n plus 2. Now what do we know? We know that n plus 2, remember, is odd. So this implies that either L or R is odd. Why is that? Well, if both L and R were even, then this value n plus 2 would be even. So either L or R is odd. So if L is odd, well then here we have an odd length circuit. It starts at v star, it ends at v star. It's of length L, L is odd, and L is less than n plus 2. So applying the inductive hypothesis, this implies that there's a cycle sitting in here somewhere. So there's some cycle sitting in here by the inductive hypothesis. It's an odd length circuit, therefore it must have an odd length cycle because L is less than n plus 2. In the other case, if R is odd, then we can sort of block out this part of the cycle. We'll look at this other odd length circuit. So we start at u0, we go to v star. We start at u0, we go to v star, and then we continue off and go back to u0. That's an odd length circuit. It starts at u0, it ends at u0. It has length r. R is less than n plus 2. That implies that there's a cycle sitting in here somewhere. So in either case, we've either found a cycle here or we've found a cycle in here by applying the inductive hypothesis to either this segment of the circuit or this segment of the original circuit. Okay, so let's prove this more formally. Even if you understood the intuition, I suggest you watch the formal proof. It can help you understand the problem even better. That's the sort of point of proving things formally. So we need to show that P of 3 and so on and so forth up through P of n imply P of n plus 2. So let's let C be a circuit of odd length n plus 2, and I'm going to write C as U0 dot 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 Vi minus 1 Vi Vi plus 1 dot 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 Vj minus 1 Vj Vj plus 1 dot 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 U0. Okay? Now, again, case 1. All the vertices in C, except for the U0 beginning and the end, are distinct. Then we're done. C is a cycle. Okay. Case 2, two vertices, or I should say, at least one vertex other than U0 repeats. Let's call them Vi and Vj. So we'll say that we have this cycle up here, this odd length circuit here, and we said that at least one vertex repeats. So we'll say that that repeated vertex is Vi, and so it repeats, so we'll say Vi equals Vj. So you take this circuit, and Vi equals Vj. You see the same vertex. Okay, so consider circuit C1, which equals U0 Vi. So I go from U0, I go to Vi, then I continue on at Vj plus 1, and I end up at U0 again. And then we'll consider circuit C2, which is equal to Vi Vj. And remember, Vi equals Vj, so this is another circuit. So since the length of C equals n plus 2, it implies that length of C1 plus length of C2 equals n plus 2. So if this were even and this were even, it would mean that even plus even would be even, but we know that n plus 2 is odd, some odd length value. So I guess case 1, the length of C1 is odd. Well, if the length of C1 is odd, it must be less than n plus 2. But remember, we assumed, this is a proof by strong induction, we assumed P of 3 all the way up through P of n are true. So if the length of C1 is odd, it must correspond to one of these P3, P5, P7 all the way up through P of n. And so by the inductive hypothesis, C1 has an odd cycle. If there's an odd cycle sitting somewhere in C1, obviously the graph has an odd cycle. case 2 is pretty much the same. If the length of C2 is odd, then it's less than n plus 2. It's odd, so it must correspond to one of these P3, P5, P7, all the way up through P of n. So this implies that by the inductive hypothesis, C2 has an odd cycle, which implies G has an odd cycle. So again, the idea was to sort of take this circuit C that has odd length n plus 2, and notice that there are kind of two circuits sitting inside of it. One is U0 through Vi, and then Vj plus 1 through U0, and Vi to Vj. Since the length of these two circuits has to equal n plus 2, one of them has to have odd length. The odd length is going to be less than n plus 2. We can apply the inductive hypothesis and conclude that there's an odd cycle sitting in there somewhere. Therefore, the entire graph has to have an odd cycle. So to summarize, if you have a graph and there's an odd length circuit, it implies that there's an odd length cycle.